So now let's get into the nomenclature. Or the naming of inorganic binary molecules. And when we say binary molecules, we mean two different elements, metal and a non-metal. So that's what we're getting into, is this nomenclature idea. And so I think an important thing to instill is, again, we've been showing a lot of the periodic table, but I think it's important to really see some of the different relationships that we have. Here I'm writing the group numbers, and then I'm just going to put transition metals. Right, and what we have here with our group 1A, 2A, and 3A, we have, a definite positive charge. And if we look at elements in like 5A, 6A, and 7A, we can say, the same thing as far as a definite charge, but now a definite negative charge, because we're on the far right side of the periodic table. So in looking at elements, I have what I call go-to elements. And so go-to elements for ionic molecules would be these groups that we're just talking about earlier. That if we have group, 1A, its charge likes to be +1. If we're in group 2A, well, now we have a +2 charge. And then group 3A, we have a +3 charge. So that's on, the positive side of the table. And then if we go over to group 7A, they like to have a -1 charge. Group 6A likes to have a -2 charge. And group 5A likes to get to a -3 charge. And so realize, once they reach that charge, they're isoelectronic with a noble gas. So that's why they're doing this particular piece. So as far as some other layers of rules here, ionic molecules always have a metal, which is positive, paired with a non-metal, which is negative. The sum of the charges must be equal to 0. Or charges have to balance out. And then also ionic molecules and their formula representation is always empirical. Right? That's just the relative ratio of elements to one another in a molecule. Right, so we have these kind of 3 different points that we have to kind of be concerned about with naming and then putting molecules together if we're actually given the name. So with ionic nomenclature, the first step is, the most electropositive element is first in the name, and basically has the same name as what we would find on the periodic table. This is always the metal. In an ionic molecule. So we have that most electropositive element is first. Same name as what we have on the periodic table. And that's always going to be the metal. The most electronegative element basically is last in the name. And basically has a suffix change. From what we find on the periodic table. This is always the nonmetal. So we have the most electropositive element, we have the most electronegative element, right? And that is last. We have a suffix change from what we find on the periodic table. And this is basically, again, always the non-metal in an ionic molecule. The suffix change is IDE, or IDE. And then the last rule, which we touched about, earlier, is just that, the number of elements in the formula basically just results from a balancing of charge, where, the net should be 0. So if we look at, maybe it's just, simple example to begin, to get a little bit more complicated here. Here we have NaCl. So we have here our metal, right? And we would see that we would have this metal of sodium. And then here we have our non-metal, which is chlorine. But we would change it to now chloride. So getting rid of that suffix for chlorine to give us chloride, and that leaves us with something we already know, right, as far as the name of NaCl being sodium chloride. Let's do another example. Here we have MgO. And to be honest, I should maybe go back to that earlier example just really quickly. Kind of remember this idea of we have 1A and that +1 charge. And we have with the chlorine here 7A and that -1 charge. So, this is why we have that 1-to-1 ratio of elements, is that charge distribution, and then also realizing that we have a balancing of charges, +1 and -1. Apologize for the interruption. Getting to magnesium oxide, right? It's the same kind of gambit. I guess I just let the cat out of the bag here as far as, well, here's our metal. Our metal here is magnesium. Magnesium is a 2A element. So that's why it would have a +2 charge. And then we have our nonmetal right here being oxygen. Oxygen's from, 6A. So we're looking at a -2 charge. Again, there's the 1-to-1. We have that balancing out. And with the oxygen, we would be doing the replacement, since it's the most electronegative, with the oxide. And so we would have a name of magnesium oxide. So simple binary compounds there. Again, that balancing of charge. Let's go the other direction. Calcium iodide, right? What is calcium iodide in terms of its actual formula, right? So we should be able to go both directions. We know the formula, get to the name. If we know the name, got to the actual formula. So here we have our still the same kind of setup, where here's our metal. Our metal is calcium. Calcium is group 2A, so it likes to have a +2 charge. And then we have our second, which is now the nonmetal. Our nonmetal here is, iodide, so that means we're talking about iodine. And we're talking about someone in the 7A group, which has a -1 charge. So in going to the formula, right, we would want to have, right, our calcium, that's +2. We have our iodide, which is -1, but we need to balance the idea of charge. And so that's why we end up with a ionic molecule that looks like this, where we have the calcium as a +2, the iodide is the -1, but there's actually 2 of them there. And so that's why we need 2 iodides. Right, we need 2 of them. So another example that's just getting a little bit, more tricky would be looking at gallium sulfide. Same, you can break it down exactly the same way, so it's not that big a deal. We still have our metal first. In this case, this is the gallium. Gallium is abbreviated by Ga. We look at gallium, it's in the 3A group. So that's one of those +3 charges that we have. And then we have our nonmetal, right? The sulfide, which is, sulfur. And sulfur is in group 6A. When the 6A is like oxygen, they like to have that -2 charge. And so there's our sulfide. So going forward, we're just putting those 2 together. We have our gallium, that +3 charge. We have our sulfide with that -2. And so now we need to balance our charge out, and that would lead us to now having gallium 2 sulfide 3 in terms of that balancing of charge. So now we have, for the 2 galliums, a total of +6. From the 3 sulfides, we have a total of -6, and so now we are actually balanced. So that's looking at binary inorganic molecules, just looking at 2 elements that make up the molecule, 1 metal, 1 non-metal. The metal always is first in the name, The nonmetal is always second in the name. And then in balancing of these, formula or deriving these formulas from the nomenclature, we have to make sure charges are balanced in terms of these go-to metals in 1A, 2A, and 3A, and these go-to nonmetals in 7A, 6A, and 5A. All right, what about now looking at transition metal? In, ionic. Molecules. And so the problem with transition metals is that transition metals can have what's known as oxidation states. And they can have multiple versions of these oxidation states. What does that mean for us? That means it means these elements can have more than one positive charge, or more than one type of positive charge. For instance, copper. Copper has, that atomic symbol of Cu, and copper can be in the +1 state or the +2 state. Or, for instance, iron, or Fe, can be in the +2 or the +3 state. So because of this, you need an additional layer. Of the nomenclature, basically, to know charge on the transition metal. And there's two systems here. There's the stock system. Stock system basically a Roman numeral follows the metal to show charge. So if I had FeCl3, if we look at our charges, we have chloride, which is a go-to element for us. That's -1. That means if we look at the chlorines, we have a total of -3. For those three chlorides, that means that our iron must be in the +3 state. Again, that balancing of charge. And so this would be iron 3 chloride. So that's how we have to designate, with these metals that aren't definitive. If it was group 1A, 2A, or 3A, well, that would be fine because they have this designated charge. They have a definite charge. But the transition metals are finicky. They have multiple oxidation states. meaning they can reach multiple different types of positive charge. So here's one example of that. And so that's why we have to use the stock system. We have to use this additional layer. Students tend to do really well with the stock system. It's not too terrible. The harder side of the coin would be then the, basically, the Latin system. And then basically using, the Latin term for the transition metal. And an IC or an IUS suffix is added. An IC suffix is the larger positive charge, for the transition metal. And the OUS suffix change is for the smaller. So we have these two things. We have an ic suffix change for the larger positive charge. We have then an us suffix change, right, when we're talking about the smaller positive charge for that transition metal. Plus it's in Latin, so students don't tend to like that too well. Going with our example above, if I look at our, our iron 3 chloride, which we know now, has that iron in the +3 state. We have our chlorides in the -1 state, so that's why we have that balanced picture. Iron +2, it would be equal to ferrous. And so that's where we see this us suffix change. And then we would have iron +3 in the ferric state. And so we see that suffix change as well. So that means in putting them together, we have, ferric chloride. So that is how we would name that particular transition metal. And so there's quite a few of them. If we kind of make a table of the metal, the Latin, and the stock, and we can do a couple sets of these. I think get them all on the page here. And so we could look at, tin. This is stannous. So it would have that, that Roman numeral 2. Or tin 2. Tin +4 is stannic. We already talked about the iron. with our notion of ferrous and ferric. And then on the other side, we could look at some of the other ones that we talked about, copper or cupric, and then the last one we could say is the mercurous and mercuric. There's more of them. There's lead with plumbus and plumbic. But here's where I'll pull basically from as far as questions on an exam is looking at these four different players: tin, iron, mercury, and copper, in terms of these types of transition metal namings. So we just have to be kind of doing the same process. It's just it's maybe a little bit different in the sense that I really want to start with the the nonmetal. So maybe a better way to represent that would be here we have a transition metal. So the first thing to do would be look at the nonmetal. Right, I know my nonmetal is 7A, and it's going to have a -1 charge. And so from the transition metal side of things, that means the tin must be a +2 as far as then that balancing of charge in the formula that's given to us. So we could say that this is tin to fluoride. Or we could say that this is stannous. Fluoride. So there's the idea with this idea of Roman numeral system, stock system, or the idea of using the Latin system in terms of naming. It's up to you what you want to really use, unless you're driven specifically to one side or the other. But as far as questions, we'll only be in that Latin system text. We'll only be looking at the ones I've talked about earlier, and I'll come back to that notion in a little bit. The last of the inorganics would be inorganic molecules with polyatomics. And so what this is saying is that not only can you have monoatomic anions and cations, you can, also have, polyatomic anions and cations. So we have, for instance, phosphate as an example. We have, a lot of these, to be honest. Sulfate, being another. Notice that these are, basically nonmetals, more than one nonmetal. That's actually starting to make, maybe a submolecule, if you will, or a substructure to the inorganic molecule that we have. Another example, just to put it on the positive side as well, we have what's known as ammonium. So please, refer to the nomenclature sheet. For, basically the transition metals, polyatomics, and general acids. That you'll be tested on. And let's just, let's actually take a look at that chart. So I guess I'll, there we go. We'll just bring it over to the side here. So we already see at the top, right here, are our transition metals. We already actually have that above in our notes. Here in the middle, we have our ion clusters, and really that's, our polyatomics. And I know it looks like there's a lot of them there, but these are very common ones that we see a lot going forward in general chemistry and organic chemistry and things of that nature. We do have some common names, hopefully you understand what water is. Hydrogen peroxide, ammonia, common cleaning agent, nitrous oxide, hippie crack, nitric oxide, right? Things that are in nitrates and things of that nature. And then the common acids that we have at the bottom. And the common acids, I think, are important because what I'd like to really help out with is, a connection. That there's a connection, in the nomenclature of general acids and basically these polyatomics. So when we look at the table, right, well, we have the transition metals. Okay, we saw the stock system, but we might have to do some memorization as far as these Latin terms. The common names aren't too terrible, but the polyatomics tends to throw students a little bit more because there's just, more of them that are actually there. And there's a lot of similarities that we see with it too, like sulfur and oxygen, but different amounts of oxygen, different charge, or nitrogen, oxygen, same gambit, different, amounts of oxygen, but same charge. So, it's kind of an interesting scenario. So what I would like to help with before we get into doing a couple example polyatomics is to talk about the connection in the nomenclature of these general acids to the polyatomics. So looking at these general acids, let's start at nitric acid. Right, so if we have nitric acid here, and we know what nitric acid is, right? What I'm trying to develop here is maybe a tool for you to use. Instead of memorizing the whole table, if I understand the general acids and then the relationship to then the polyatomics, it's actually going to save me a lot of effort in memorization that I actually have a tool set to actually use to get to the answer. So if we look at HNO3, realize this is like any type of metal, non-metal, meaning here is our metal. I know it's weird because of our hydrogen, but this is a 1A element, so it has a +1 charge. And now with the polyatomic, the whole thing has to now balance our charge. So the nitrate is going to be completely -1. So there is our polyatomic. And it's not, on the oxygen, right, in terms of this representation of formula, right? It's on the actual polyatomic itself. So we have the nitrate there. I apologize to keep saying that. The NO3 there. We have our +1 hydrogen. And so that's a breakdown, meaning that, okay, if I go forward, I now know I have something that looks like this. I'm just kind of leaving out the metal portion of the thing, right? Because that's actually leading me to the polyatomic. I know this NO3 must be -1 charge because the nitric acid molecule HNO3, well, the hydrogen's +1, and that's where that -1 charge comes from. And if I scroll back up a little bit, I apologize, we find that we have NO3 -1 is right there. And all I need is a suffix change to nitrate. So I start with the nitric acid, and then I end up with nitrate, simply by removing that proton, that hydrogen that's +1 charge. If I know that polyatomic with the nitrate, I can now go one step further and basically now, lose 1 oxygen, same charge, and now I end up with nitrate. Again, another polyatomic that I have. So if I go back up to that table, I find both of those right next to one another as far as the nitrate and the nitrate, which is a simple loss of an oxygen. We can do the same thing with sulfuric acid. If I do the same kind of process, right? My hydrogen here again is that kind of metal representation. It's 1A has a charge of +1. And so my non-metal here is really a polyatomic, and that's where I need to balance my charge, which would be SO4, then -2. Right, there are two hydrogens, both are +1, so the SO4 must be -2. And now taking that name as far as what is this SO4 -2, well, that would be sulfate. So just like before, that ick from the sulfuric acid turns to 8. Right, so here is our polyatomic sulfate. And if we do the same process, right, where we're going to basically be, we're going to lose one oxygen, have the same charge, we end up with SO3 -2 or sulfite. So again, there is our polyatomic. There is our suffix change. And I'll scroll back in a sec, but just to bring you back up to the table, we see that here with our sulfate and our sulfite. And you can go through a lot of these other ones like acetate and carbonate, bicarbonate, chromate, it's all, perchlorate, it's all the same motif. So that's, naming with these polyatomics, and I'm just here trying to, develop a method here to maybe help with all the different polyatomics that I'm asking you to know in terms of, a test scenario. Just maybe as, an example of, something really tough. We could ask, what is the name of this Fe3PO4? And so this would be really kind of the highest level of bringing, not only this idea of polyatomics together, but also the idea of transition metals as well. And if we look at the PO4, we could actually think about it in terms of what I was just describing above, that if I put hydrogens there, I know that this is actually phosphoric acid. So that means my polyatomic that I have here must be phosphate. Right, just like we went from nitric acid to nitrate and sulfuric acid to sulfate, well, here we're going from phosphoric acid to phosphate. So there's our non-metal portion, and it has that total charge of -3. That means our iron must be in a +2 state to balance out charge. So that means we would have, as far as our name, we could say we have iron 2-phosphate, or when we get fancy, we would say ferrous phosphate. Right here is our stock system. Here is our Latin system. Latin system in terms of that nomenclature. So that's inorganic naming, from simple binary compounds of definite charge to transition metals where we have, multiple possibilities, and we rely on the nonmetal to help us know what charge we're in for the metal. And then the most complicated is the polyatomics, but I think a good tool again is if you know those general acids, and you follow that routine of losing the hydrogens and assigning the negative charge. You'll find that might be a hopefully find that is a good tool to help in minimize the memorization of the table, and so you have a tool to actually allow you to go further in this naming process.